Okay, let's now have a look at part B. So part B, we're asked to calculate the p-value and interpret its meaning. Now remember, p-values are an alternative way of coming up with your hypothesis test decision. And the way it works is we must have the test statistic to be able to calculate the p-value. Now our test statistic, as we calculated in part A, is 2.4. So you can see I've drawn 2.4 onto my Z diagram and I've shaded in the area above that. Now, because this is a two-tailed test, getting a test statistic of 2.4 is equivalent to getting a test statistic of negative 2.4. We would have reached exactly the same decision given it's a two-tailed test. So I've also marked that area onto my Z diagram. Now in terms of, I've got to find that total area. That is what the p-value represents. The p-value, if you look at the diagram, it's the shaded area. The upper tail above 2.4 and the lower tail below negative 2.4. So where do I find that area? Well, it's symmetrical, so the upper and lower shaded areas are going to be exactly the same. I can use my Z tables, just the first lot of Z tables that you have, and in fact I'm going to work out the lower tail area because that's the one I can look up most easily in the tables. I look up a Z value of negative 2.4 and it tells me, or the tables tell me, that the area below negative 2.4 is 0.0082. So that's the lower shaded area. Of course the upper shaded area is the same amount. So if I want to get the total area, just multiply 0.0082 by 2. We come up with 0.0164. So not quite 2%. So that's my p-value. And we've been asked to interpret the meaning, but we can certainly, I think I've said this as we've been going through, but I've got it typed up for you. When you look at a p-value, it's the probability of getting a test statistic, well, in this case, of 2.4 or more extreme. So that's what it's representing. So our p-value is telling us that the probability of getting a test statistic of 2.4 or something that's more extreme is 0.0164. Not quite 2%. In terms of how we would actually use that to come up with our hypothesis test decision, well, remember we can compare p-values to the alpha. So in this case, our alpha was 5%, that was the size of the reject region. And because our p-value fits inside that, because the p-value is less than alpha, we reject the null. It's exactly the same decision as we got in part A. So part of part B is to show you that we end up with the same decision. It's also just to remind you how to do these calculations. But that's the comparison you make. You compare the p-value to alpha. If the p-value is less than alpha, you reject the null. If it's greater than alpha, you don't reject the null. And the reason we're rejecting here, p-value is less than alpha, that's telling us that those shaded areas that we just worked out fitted inside the reject region. Because they're smaller than alpha, they fitted inside the reject region, so our decision had to be to reject the null. Now, part C asks us to have a look and say, well, okay, if our alpha was 1%, what decision would we make? Now, because we've already done the p-value in part B, changing alpha is now really easy to come up with our new decision. We don't have to go back, redraw the decision diagram and compare our test statistic to it. We can simply compare the p-value of 0.0164, that's the p-value, it hasn't changed. If we change alpha, well, we just do a new comparison. And this time our p-value is greater than alpha. So that's saying that our test statistic did not fit inside the reject region, and so therefore we don't reject the null. So as well, I suppose this question is also just as a reminder to you that the level of significance, our alpha value, is quite important. It can impact your decision in this way. A different alpha can sometimes mean a different decision. And remember, alpha is representing the chance of a type 1 error. So if we want to reduce that chance and have an alpha of just 1%, so a 1% chance of type 1 error, so a more accurate test, in this case our sample evidence is just not strong enough to go against the null. So part C, we're not rejecting the null, and we could do that nice and quickly because we could compare the p-value to alpha. So that was part C. One last thing to have a look at is part D. So part D says, what is your answer in B if the standard deviation is $24? And in fact, I think this should have said, I think my slide's wrong, it's what is your answer in A if the standard deviation is $24? So we basically want to go back and redo the question, still with an alpha of 5%, so our decision diagram is not going to change. We just want to change our population standard deviation sigma to $24. Now, you can just plug the new number into the test statistic and recalculate, and you can see we've done that there. So it's now still same sample mean, 172, same hypothesized population mean of 160, divide by standard error, sample size hasn't changed, only sigma, so it's now 24. If you do that, you get a test statistic of 3, and that's still within the reject region, so at alpha of 5%, we're still rejecting the number. So why did we get you to redo this for a different sigma value? Well, I suppose just wanted you to be able to see how the test statistic changes depending on the value of sigma. Now, our original sigma was larger. So when we reduced our population standard deviation, you can see the impact it's had on the test statistic is to increase the test statistic. Our test statistic has gone from 2.4 in part A to now 3. And that's because a smaller standard deviation, and remember a smaller standard deviation is just the same as saying less variation in the population. So if we've got less variation in the population, what impact that has when we do a test statistic is, well, our sample result is now further away from our hypothesized mean of 160. So our sample result of 172, if the population standard deviation is less, well, 172 is now further away from 160 in terms of, measuring that distance as a number of standard deviations. So that's why we get the larger test statistic, because the test statistic is pretty much telling us how far away the sample result is from the hypothesized mean relative to standard deviation. So when the standard deviation decreases, our sample result seems further away, and that's why we get the larger test statistic. So you could have just done part D by recalculating, but I think it's nice just to have that little bit of a chance to think about how all of these quantities relate to each other. So that's a nice sort of logical addition to the problem.